Carbon capture, utilization and storage is a very important topic, especially in context of blast furnaces where emission level is extremely high. So CCUS, we can say that it's a method used to reduce CO2 emission from industries like steelmaking. So let us see how it works step by step. Generally, the problem arises especially to trace that where the system is to be installed and which will be beneficial. So before coming to the commissioning of a system, it is better to understand how the network of the blast furnaces in particular work. So now this is about our blast furnaces, how the furnaces outgoing gases travels. So the blast furnaces produces hot gas full of CO2, and of course it is not full exactly full of CO2, especially 22 to 25% we can say at a rough estimate is around this percent of CO2 remains in blast furnace outgoing gases. This gas goes through several stages. BF top, you can say that raw gas is created. It going to dust catcher. In dust catcher, the big dust particles are getting removed, and thereafter whatever remaining is there, that goes to a water scrubber. Especially we use water to clean fine dust, and the carryover gases which with the moisture enter to demister to remove water droplets, and then finally this gases moves to top recovery turbine where the gas pressure is utilized to generate electricity. So after these, the gas is split and used in different places like hot blast stoves or power plants. Now coming to capture CO2, we first calculate how much is produced, and we use formula based on the gas volumes and the furnace input like coke and oxygen. For example, a blast furnace producing 3,000 tons of hot metal per day generate about 1944 tons of CO2 daily, and a special capturing formula is also incorporated in this presentation in a later half. So to the capture CO2, we use a plant with absorber and a stripper columns. These uses a chemical called MEA to absorb CO2. The plant need about 130 tons of MEA per day and handles around 4.5 million cubic meters of gas daily. So we can imagine what sort of mammoth unit is there which is handling such type of system. So here we come across the volume of gases about which we are talking, and we can formulate up to a rough estimate can be find out in this way, that whatever oxygen you are, a specific oxygen you are using, then what is the coke rate, whatever is the PCI rate, and this any hydrogen injection, of course the component from the PCI and steam has been overlooked as not counted in this calculation. So based on this, we can find out what is the approximate top gas volume, and what sort of what is the CO2 load in top gas is there. So this is all we can see here. What sort of solvent will be required based on the CO2 load. This is a sort of a calculation sheet shown. Now coming to the power requirement, running the capture plant requires electricity of huge quantity, and about 8 megawatt daily electricity will be required. So these power pumps, blowers and heaters needed to process the gases, and a short of a sheet, calculation sheet has been provided. Now coming to the system which fed the cooling water need. and this is also a very important system in the CCUS total integrated project. The system need the cooling water around 3,900 cubic meter per day, a good volume of water to keep the chemical reaction stable and efficient. And water is one of the most important ingredient in running the system smoothly. So a full scale CO2 capture plant need around 2000 to 4000 square meter of space. This is basically a rough estimate of the plant network for area and equipment. It include tall column, tank pipes, and pumps, and especially the cost. As far the cost is concerned, the cost is huge. The cost is around 500 to 8,800 crores to build, and around 2,000 to 3,500 per ton of CO2 to operate. So it's a tremendous value, and it need to be carefully evaluated whenever we are going for installing this. And this is basically different ways to capture this CO2, and this is basically gives us a idea that which system, which methodology, which route is supposed to be a better in the context wise. So it need to be carefully evaluated and see like MEA, that which are the very common, and this here we get a high purity high purity this CO2, and similarly MDA or MP uses less energy membranes and easy to maintain, simply cryogenic, that is for very pure CO2, and calcium looping is still being tested. So these are basically the status of the different technological levels of the routes or ideas. And this is all about the steam requirement, and which is also very important, because the steam is one of the most important ingredient and parameter in the CCUS project. So most energy is used to generate the most energy is used to generate the solvent. This MEA needs about 3.5 to 4.5 gigajoule of steam per ton of CO2, and for our example, that's around 79 megawatt of steam daily. So we need to a strong boiler or a steam source for this project. And in the summary table, we can say that here is a C1944 TPD gas volume, for which we need around 4.5 million normal meter cube per day. MEA MEA needed will be 130 TPD. Steam, as for this project is concerned, 79 megajoule. Power will be 8.1 megajoule. Water will be around 3,900 meter cube per day, and cost will be around 800 crores. So this is